Hello! Welcome to today's session on correlational research. As always, please make sure that before you begin watching this video, you have the PowerPoint lecture notes printed in front of you so that you can take notes as you see appropriate. Secondarily, we also want to make sure that you're near a computer while you're watching this, a computer that can display the PowerPoint presentation, so that you can zoom in and see some of the details as you need to. As we begin our conversation today, I'll just remind you that we'll be talking first about descriptive statistics, and we'll go over some information that we've had in prior lectures, but we'll also learn a little bit of new information that will help us to better understand correlational research. And then we'll introduce correlational research, and we'll tell you a little bit about the Pearson R statistic. We'll show you some of the components that go into the R statistic. This was discovered by Carl Pearson. And then we'll set the stage for something that we'll do in class for our hands-on exercises, where we will be in Excel computing the R statistic manually. So let's go ahead and get right into it and remind ourselves a little bit about the context in which we're operating. As often is the case, we like to start out with our research cycle, and we have these 4 different boxes that are spread throughout this entire diagram. And you can see that we want to look first at some real-world phenomena. We have to abstract using operational definitions and sampling to create some kind of manageable research representation. That being the case, then we can proceed to some kind of methodology. And you might recall that this semester, we're talking about 3 different kinds of methodologies. The first is observational, then we'll be talking about survey methods, and then finally we'll be talking about experiments. After we have taken some methodology, we generate some research results, and we have to analyze those results, and that's what we'll be doing today with respect to the R statistic. We'll be learning a lot about correlation. This will give us some conclusions that we hope will generalize back to the real world. So today, most of our emphasis is going to be here on data analysis. We've mentioned descriptive statistics before. We've talked about the importance of having some kind of indicator of central tendency and some kind of indicator of dispersion. So in this chart, we have our indicators of central tendency and dispersion, but we want to make a distinction between what we might do for a sample and what we might do for a population. And we'll define these terms again. In an earlier video, we had defined a population as every member of a group of interest. Sometimes, though, that gets a little bit unwieldy, and we can't investigate every member of a group of interest, so we have to take a subset, and we call that subset the sample. Whether we're describing a sample or a population, we always want to be able to provide some kind of indicator of central tendency. And so in this case, we're going to be talking about means. And when we have descriptors for the population, we call those parameters. And we use population parameters in descriptive statistics by showing Greek letters. That's the convention in our science. And we would use the Greek letter mu for the mean of the population and the Greek letter sigma for the standard deviation of the population. You might remember that when we square the standard deviation, we come to the variance, or equivalently, we can take the square root of the variance and we would come to plus or minus the standard deviation. And this is the symbol that we would use, or set of symbols that we would use for population parameters. Equivalently, in the domain of the samples, when we're looking at just a subset of every member of that group, we still want to describe the mean and the standard deviation, but we would use either a lowercase English m to indicate mean, or we might use an x bar or this English letter s for the standard deviation. If we square that, we have s squared, which would be the variance. The square root of the variance is going to be plus or minus s as our standard deviation. So just a little bit of terminology there. Now we might ask ourselves, under what conditions would we choose to use the mean as opposed to some other indicator of central tendency? And that brings us to this graph. Here, what we can see is that we have different measurement scales, and we had introduced these in a prior lecture also. We actually have 4 different kinds of scales, but in some software packages, we take these last 2, these are the most refined scales, and we combine them. So we actually wind up with 3 functioning different kinds of measurement scales. And we might say that about the nominal scale, our preferred central tendency is the mode, and it doesn't really make sense to talk about the dispersion when we have such a rudimentary scale. But we can begin talking about dispersion once we get a slightly more refined scale, and we're up to either an ordinal scale or a rank scale. And usually the preferred indicator of central tendency in this case is going to be the median, and the preferred indicator of dispersion is going to be the range. You might recall that was the difference between the maximum score and the minimum score. Finally, when we get up to these very highly refined scales, the interval and ratio scales, which again are combined in some software packages as a single scale, we generally prefer the mean, and we generally prefer the standard deviation as our indicators of central tendency and dispersion. When the distribution of scores is skewed by a few outliers, the mean and standard deviation can be misleading. A median and range are preferred, and then we might ask you to stop the video and see if you can generate some real-life examples of skewed distributions. We've given you a few in prior lectures. We'll see if you can generate either those again, or even more preferably, some examples of your own. Okay, welcome back. So now we'll proceed, having built on this idea of central tendency measures and dispersion, we'll proceed to talk about correlation, and we'll remind ourselves of something that we hope you had taken away from your Introduction to Psychology course. One of the main themes there is that correlation does not imply causation. In fact, we're going to make that a mantra. Say it with me. Correlation does not imply causation. That's a very basic principle that we learn in Intro to Psychology. What's a little bit challenging for some students is that although correlation does not imply causation, correlation actually is a necessary but not sufficient condition for causation. So we have to try to keep all of those relations straight as we're proceeding in our conversation about correlation. We can conduct a correlation, and when we are conducting correlations, we're looking for an association between two variables. We sometimes use those words interchangeably, correlation and association. And we might say that if we're looking at two variables and asking whether they're correlated, we wanted to know if particular values on one variable might be associated with particular values on another variable. So one way to think about that is if we have two variables, for example, we'll take a simple psychological set of variables. We might think about anxiety, and we can measure anxiety lots of ways. We can measure anxiety by how much you're sweating, using something like a galvanic skin response. We could measure cortisol levels, which can be sampled even from saliva. We could measure heart rate, we could measure breathing rate, lots of different ways of measuring anxiety. We could even use a survey to measure anxiety. And we want to know if there's a correlation between anxiety, however we choose to operationally define that, and maybe the difficulty that we have in concentrating. And we might use even something like a survey to get a self-report on the difficulty that people are having with their concentration. And we can ask about the correlation between these two variables, anxiety and concentration difficulty. It might be the case that we have an association such that maybe high levels of anxiety are associated with low levels of concentration difficulty, or high levels of anxiety are associated with high levels of concentration difficulty. There might be, though, no association between the two. That is, high scores on one variable are not necessarily associated with either high or low scores on the other variable. It might be a bit of a random association, and then we would say that we have very low correlation between those two variables. Before we begin looking at the computation for the R statistic, there's a few things that we want to make sure that we have completed before we begin that, and one is that we want to clean up the data set. And we've mentioned this before, but I want to emphasize it here again. There are actually two ways that we want to clean up the data set. First, we should always look at our data set and see if we can identify any impossible scores. These would be scores that land outside of the variable's range. Okay? So we can think of different kinds of examples. If we're talking about height, for example, we might say that height can be expressed in centimeters, height can be expressed in inches, but heights really can't be negative, at least in any kind of absolute sense. So if we had a list of numbers in our height variable column, and we saw there were a couple of negative values in there, we should be very suspicious about those. That might be some kind of data entry error, and we need to factor those out or actually just throw those data points away before we begin our correlational analysis. So we want to make sure that we're in range. Okay? The second thing we should do is clean the data by excluding outliers, scores that are very different from the others. Okay? So you can imagine that we might have the case where a few outliers could strongly skew the mean and strongly skew the standard deviation. It turns out that when we compute the R statistic, we're going to be basing the R statistic in part on the mean. That'll be one of the first steps in our computation. And if the mean is off because of a couple of outliers, then our R statistic might turn out to be very, very misleading. So if we have some scores that are very different from the others, we might want to exclude those. Now you can ask, how do we operationally define very different from the others? That is, how wide a difference or how large a difference would we need to exclude certain kinds of data? There are different ways of coming to such rules and developing procedures for excluding data. Here's a moderately common one. We might ask about scores that are perhaps 3 standard deviations away from the mean. And we might say that those scores are so extreme that they might be skewing a data set. Especially if it's a smaller data set, we'd be very concerned about that. We'd be especially concerned if those outliers were consistently on one side and not the other of the mean. This would introduce a rather dramatic skew and would make the mean very misrepresentative. And once we have a misrepresentative mean going into our correlational computation, you can imagine that the resulting correlation is also going to be skewed and misrepresentative. Okay? So once we use this kind of a rule where we typically factor out something that's 3 standard deviations away from the mean, we generally clean up the data set, and such scores typically occur in a normal or Gaussian or bell-shaped curve, fewer than or less than 1 time in 1,000. So it's relatively safe to exclude these, and we might be especially careful about this issue when we have smaller numbers of observations. Okay. One more note about excluding data, and this is a little bit ironic, but the decision not to exclude data can sometimes produce very misleading results. Now, you might have been instructed by professors to keep all of your data in your data set and not just throw data out, and in general, that's a good rule. It can be considered dishonest, as a matter of fact, to exclude disconfirmatory data points. We want to show all the data under most cases. But there are cases, and we can think of some examples perhaps, where we have some very extreme scores that are throwing off the data and maybe are even going to generate a correlation that wouldn't otherwise be there were it not the case that we had these outliers. So we want to make sure that we're not introducing a phony correlation just because we happen to have a couple of highly misrepresentative points. Okay, so once the data have been cleaned, that is, we've eliminated the impossible scores, we've looked at very unusual scores and thought about very carefully and very judiciously whether that might give us a skew in our data. Okay? After we've cleaned that up, then we're ready to take one more look at descriptive statistics. We'll create means and so forth. And we might show these graphically. So here, we might have something like our data have been cleaned up, and we can talk about the anxiety that we're experiencing and the concentration difficulty that we're experiencing. And we can then go on to graph those data through something like a scatter plot. And for a scatter plot, we typically have one of the variables on the x-axis. We call this our predictor variable. We have the other variable on the y-axis. We call this our criterion variable. And for any given score, we'll plot the intersection, or for any given participant, we'll plot the intersection of those two scores. So for a particular participant, we might have an anxiety score of 8, and we might have a concentration difficulty score of 4, and so on down the line for each of the points that we have here. So we would call this a scatter plot. And sometimes, just by inspecting the data visually, we can see that there's a trend that might be emerging here, that maybe the data are forming a relatively upward trend or a downward trend, or maybe there's no linear trend at all. In today's conversation, we're talking about correlation, and we're really talking about linear correlation. As we'll see shortly, there are other kinds of correlations as well. Okay, so very often the scatter plot is presented along with an R statistic, and we're going to work our way toward computing the R statistic. The R statistic is typically indicating the strength of the linear trend in the data, although you can use R statistics for other kinds of trends as well. But in this introductory course in research methods, we'll be using R almost exclusively in the linear case, and that's what we'll be describing today in our video. Just as a reminder from Intro to Psych, you might want to stop the video and see if you can answer this question. What is the range of possible R values? Okay, welcome back. The answer to that question, in case you're not entirely sure, is that the R value can range from -1 through 0 to +1. So -1 to +1 would be our full range. Sometimes in science, including psychological science, we square the R, and then R squared would obviously range from 0 to +1. But R itself ranges from -1 to +1. Okay, so here we have a few different kinds of scatter plots, and for each panel above, you might identify one plausible R value and identify also one implausible R value. Okay? Now remember that R ranges from -1 to +1, so we might take a look at this relationship where we have anxiety and concentration difficulty, and look at the data plotted in this scatter plot and see how would the best fitting line fit here. Okay? How would the best fitting line fit here, and how would the best fitting line fit here, and then we might give ourselves an indication of what the R statistic is. Okay? So we'll let you think about that for a moment. Okay, and what I'm going to do is see if I can jot on the board here. Clear this up. Okay, now we're projecting our graphs onto a writable surface, and what we might try to do here is find the best fitting line. So I'm just going to freehand it, but you might see that there's a bit of an upward trend. So I'm going to do something like this, and I might be off by a bit, but that might be something like the best fitting line. Okay? And so a plausible R value here would be some R value that is greater than 0, but not all the way to 1. And the reason we don't go all the way to 1 is every one of these dots would have to be right on the best fitting line. They'd have to form a perfect line all by themselves. To the extent that there's scatter around that line, we start moving away from +1. But clearly, we have a slope that's measurably different from 0, and so we're probably going to have plausible R values of maybe something like 0.4, 0.5, something noticeably different from 0, but not all the way to 1. We can do the same thing over here. We can find the best fitting line. And that one might be a little bit better. You might see that we have a relatively strong negative trend. It doesn't go all the way to -1 though, because if that were the case, every one of these black dots would be right on the line. Okay? And then finally, we might say over here is that we don't really see any particular linear trend. The best fitting line might be something like this, almost perfectly flat, and a good R statistic over here would be something very, very close to 0. It might be marginally positive or marginally negative, but we probably have an R value close to 0 here, relatively strong negative here, and the absolute value of that might even be stronger than the absolute value of this because we have less scatter here than we have here. Okay? All right. Let me get rid of those lines. We'll bring this back down. Okay. Now, we can also ask about some other types of patterns that we might have, and we might ask, what do you suppose the R value would be in these cases? So why don't we give you a moment to stop the video, see if you can find the best fitting line, and take a guess as to what a plausible R value might be for each of these two scatter plots. Okay, welcome back. Now what we can say here about this one on the left is that you probably can fit something like an upward trend. An upward trend would fit better than what a downward trend most likely, although not by a whole lot. What's interesting here is we have a pretty good pattern, pretty obvious increase to start out with, then a decrease followed by an increase again. And we might say that this is something called a cubic trend. A cubic trend has two bends in it. You can see that we're bending around here. There's our first bend, and now we're bending back up. Okay? And we'll show you the equation for that in just a moment. So we have a couple of bends that take us away from a linear trend. All right? So we have a curvilinear trend here, and it's going to be one that we describe as a cubic trend, and from time to time you might see this in psychological research. We go over to this one, we again would probably see that we don't have a really good fitting straight line. In fact, the best fitting linear function would probably be just a flat line right about here. It wouldn't make a real good fit. On the other hand, there appears to be a really nice curvilinear trend that we might call a quadratic trend. So I'm going to raise this one more time. We'll see if we can draw the best fitting lines, at least approximately, and then we'll give you an idea about what a cubic equation might look like and what a quadratic equation might look like. So here you might see that we're going to go up, down, and over. So I'll just draw that very crudely here. And that might be the best kind of a trend. And you can see we have one bend here. We have one bend here. And whenever we have two bends, we say that we have a cubic trend. So you might remember from high school that you had done some work with polynomials, and we'll give you an example of a polynomial equation that might work for something like this. We might say that a good equation here is y equals ax cubed, and that's where the word cubic comes from. Cubic would imply that we have 2 bends, plus bx squared plus cx plus d. Okay? So this would be the equation for the best fitting line in this particular case, or the best fitting trend, I should say. You might remember that y equals mx plus b describes a straight line. Here we have a curvilinear trend, and it's cubic. We have 2 bends in it. It might be an equation of this form would fit these data quite well, whereas a straight line probably wouldn't fit quite as well. We'd have quite a bit more scatter around the linear trend than we would around this cubic trend. Okay? Let's take a look at this. On this side now we have a pretty good curvilinear trend that goes up and then down. This is fairly common in psychological research. We get these kinds of trends, and you might remember doing some quadratic polynomials in high school. So this might be something like this. Y is equal to negative ax squared plus bx plus c. Okay? And that's negative. When the leading coefficient is negative, we typically have this type of a curve. It's an inverted U, and you can think of it this way. When we have a negative leading coefficient, we have a negative face or an unhappy smiley face. If this were positive, then this would be more like a smile. It would be facing upward rather than downward. So we hope that's a helpful mnemonic for you. Now, what we could do is we can ask, what is the R value associated with this very complicated trend? And that would be a pretty strong R value. It would depart from 0 by quite a bit. And the same thing would be true here. But neither of these would have a very strong linear trend. The best fitting line is going to have a lot of scatter around it in each of those cases. Okay, let's bring this back. And now we'll begin talking just a little bit about computing the R statistic, but what I'll ask you to do for the moment is stop the video and jot down what you think to this point has been very clear to you, and also what has been less clear. Okay, let's see if we can now introduce some of the computational components in Carl Pearson's R statistic. So some of these are old friends to us. We've seen some of these before. The Pearson R statistic is based on 3 quantities, SSX, which we've done before. That's the sums of squares for our x variable. Then the sums of squares for the y variable, and we've done that in a prior video. Here's our new term. This is called the sums of products, or SPXY. So the first 2 quantities, sums of squares, are not at all new to us. We've done this before. We've had a computer quiz on this. Okay? And here's just a reminder of how sums of squares will work. We're going to take a particular observation. Maybe that will be from our x variable. We will subtract from that observation the mean of that set of scores. So that might be the x mean, for example. And we're getting a deviate here. To what extent does a score deviate from the mean? And we're going to square that difference. This allows us to get rid of all the negative numbers. And then we repeat that, summing up all of these squared deviations. And this allows us to get a sum of squared deviations for the x variable. And then we repeat that exercise one more time for the y variable. And we'll have 2 sums of squares to work with, one for x, one for y. Okay? The new quantity that we'll be talking about is the SPXY quantity called the sums of products. And unlike the sums of squares, the sums of products can be negative or positive. So the sums of squares can be either 0 or positive, but it can't be negative. And this is because the sums of squares is derived by taking many different numbers, all of which are squared, and they are then summed up. So we're either winding up with zeros or positive numbers. We never can get a negative number so long as we are in the real number system. There is such a thing as the complex number system. You might remember learning about imaginary numbers such as the square root of -1, but that's beyond the domain of this course. We're going to be talking about the real number system, so our sums of squares will either be 0 or positive. It will always be non-negative. Our sums of products, though, can have either a positive or negative sign. And the sign, positive or negative, of the SPXY term will be the same as the sign of the R statistic. So we said that R can range from -1 to +1. That sign will be driven entirely by this term, the sums of products. Okay, so we'll begin to introduce some of the steps needed for computing the SPXY. For a given pair of x and y scores, we have to do the following. Okay? We have to find the difference between x and its mean. We have to find the difference between y and its mean. So let's see if we can give you a very simple example. Earlier in the video, we talked about the possibility of looking at the relationship between anxiety on the one hand, we might make that our x-axis, and concentration difficulty. Okay? And so for you, if you are the participant, we would get an indicator of your anxiety score, and we would difference your score on anxiety from the mean anxiety score, and we would have a deviate, or a difference score on anxiety for you as an individual. We'll hold on to that number. That's going to be our deviation for the x variable. Then we would repeat that exercise on the y-axis. And that's to say that we would take now your concentration difficulty score for you, and then we're going to subtract from that the mean concentration difficulty score, and we get a deviate score there on your y. So now we have a y-axis deviate for you and an x-axis deviate for you. We have those two deviates. We would multiply them together, and we'd come up with some product. A product is what we get whenever we multiply two numbers. Here we're multiplying two deviations, one from the x, one from the y, and that's how we get our first deviation. We multiply those two together, and we repeat that for each score that we have, and then we sum those up to get the sums of these products. Okay? So computationally, this might look like this is challenging, but it's really not that bad. We took your score, we subtracted from it the mean, and this was on the x-axis variable, which again was anxiety level. And we're going to multiply that difference by the difference score that we obtained on the y-axis variable, which was concentration difficulty, your score minus the mean. And we repeat that for every participant that we have in our study. We sum all of those up, and we wind up with a sum of products. What we have down here is a simple mnemonic that some of you may have been introduced to in high school or maybe even junior high school. It's PEMDAS. That's P-E-M-D-A-S. And you might remember this as please excuse my dear Aunt Sally. Okay? And what it's giving us is the order of operations. So we always start with parentheses first, then we move on to exponentiation, and then after that we do multiplication and division before we proceed to addition and subtraction. That would be the order of operations in all mathematics, and certainly we follow this as well here for the computations that we're doing for the R statistic. Okay. So here's a thought exercise for you. Thinking about this particular mathematical expression, when would this expression produce large positive values? And when would this expression produce large negative values? We'll let you stop the video and think about that, and look forward to your answers in class. Okay, we'll move on. And here then is the R statistic with all the components that we need for its computation. So the R statistic can be defined this way. SPXY, which we just computed in the previous two slides, divided by this relatively large denominator term. We're going to take the square root of the sums of squares x times the sums of square y. Okay, so we have quite a bit going on there in the denominator, but we really have very simple components. It's just a matter of mixing and matching them appropriately and making sure that we know the order of operations. We're going to multiply these two together first, and then we're going to take the square root of that product, and that's going to be the denominator that will get divided into our SPXY from the preceding slide. Okay, and we'll come up with some kind of an R. Okay. Here's an interesting thought question for you. Can you explain why the sign of the R statistic has to come from the numerator and not the denominator? We'll see if you can think that through and put a brief response into your own words. We'll let you go ahead and do that. Okay. And then what we'll do is we'll head on off to Excel. In the classroom when we're together, we will take a range of anxiety scores and we will correlate them with a range of concentration difficulty scores by computing the SPXY, or the sums of products. We'll also get a sums of squares here and a sums of squares here. We'll put those quantities into the formula that we saw on the preceding page, and we'll be able to manually compute the R statistic that shows the association or correlation between these two data sets. So what I'd like you to do now is to get prepared for that computation. We will always want to make sure that you have some good intuitions about how this is working. So please be sure to write down what was clear in this presentation and also what was less clear. And I look forward to taking your responses in class. See you in class.